For this video, we're going to look at how to do a hypothesis test for one population mean when sigma is unknown. As we talked about when we were working with confidence intervals, it is more common to not know sigma than to know it, because if you knew what sigma was, if you knew the population standard deviation, you would also know the population mean, in which case you wouldn't need to estimate it with a confidence interval or do any hypothesis test. So just like with our confidence intervals, we are going to use our t-table. We're still going to have degrees of freedom as we did before. The biggest difference when doing a hypothesis test with your t-test statistic and using the t-table is getting your p-value, because as you know, your t-table doesn't have as many values on it as the z-table. So if you're using your tables, it becomes a little bit more difficult, and we have to do an estimate for our p-value as opposed to our regular p-value. Now, of course, if you have a graphing calculator, you can get, or you can hop on the computer, and there are free websites that will give you exact p-values. But most of you are going to be using the table, so let's take a look at how we would do that. So let's suppose we ran a hypothesis test and our t-test statistic was negative 1.938, as shown here, negative 1.938. We have a t-curve. We know we have, since it was a sample size of 12, we know we have 11 degrees of freedom. Normally, when we're working with the z-table, you would just look up that test statistic and get the exact area to the left of the curve, which your table will give you. But if we try to look up the 1.938 at 11 degrees of freedom on our t-chart, let me go down to the t-chart. I'll get rid of what I had highlighted before. So again, we're at 11 degrees of freedom. We want 1.938. I know we want negative, but recall that your t-table does absolute values, so whether it's negative or positive, you're just looking up 1.938. So here, let me highlight the row with the 11 in it. That's not quite what I wanted to do. Hold on. Okay, there's our 11 degrees of freedom. So 1.938 does not fall. We have 1.363, 1.796, 2.201. So 1.938 is actually going to fall between those two values. Okay, so this is how this is going to work. If the test statistic was 1.796, it would have an area of 0.05 to the left. If the test statistic was 2.201, it would have a smaller area of 0.025 to the left. Now, and you can kind of see this in this second picture where they're showing the 1.938 and they're showing the other two areas. So at 2.201, this is your area in here. And then at 1.796, that is your area. So clearly, the area of 1.938, regardless, again, if it's negative or positive, that doesn't matter, is going to fall between 0.025 and 0.05. So here is our 1.938. Okay, recall the area is 0.05 for this number, and the area is 0.025 for this one. Be careful, because this is what I want you to notice on your t-table. As your test statistic values, your t-scores go up and increase, look what's happening to your areas. The areas are these small values, subscripts of the t's. They're going to go down. Okay, because, and that makes sense, because if you think of a standard curve, this might be 1.3 and here's 2.2. Well, 2.2 is going to have a much smaller area than 1.3 is going to have. So just please make sure you're reading it carefully. So with 1.938 being between 1.796 and 2.201, the area is between 0.025, because we always state the smaller area first, and 0.05. So what that tells us then is this p-value right here for the negative 1.938 is between 0.025 and 0.05. And while that does not give you an exact number, remember, all we're looking to do with our p-values for this particular class is to compare them to alpha. So again, this is what you would state for your p-value. You would give the range, and then you would say what alpha is. So let's suppose you were working out a problem where your alpha, your significance level, was 0.05. If alpha is 0.05, clearly we can see p is less than 0.05. And remember, when p is less than alpha, we can reject. So let's take a look at one that's two-tailed, because in that case it gets a little bit trickier because we have two different areas. Same idea, t of negative 0.895 or t of 8.895 with 24 degrees of freedom. So we want to go to our t table, where the 24 degrees of freedom row, and look up 0.895. So now we're going to go down to, let me just double check. Yeah, sample size 25, so we have 24 degrees of freedom. So we're looking at this particular row right now, and we're looking for the number 0.895. Well, the smallest t value we have is 1.318, which has an area of 0.10. So that means in this case, our 0.895 is smaller than the smallest t value on the table. So be careful now. Remember what I said before, as your t values increase, your areas decrease. So since 0.895 is over here, look what's happening to our areas. So you have to think about this. Does this mean p is less than an area of 0.10 or greater than an area of 0.10? Follow the chart. As you move to the left, your areas are increasing. So as your t-test statistic goes down, becomes smaller, your area is actually going to increase. And that makes sense, because 0.895 is going to be an area very, very close to 0. So clearly that is a much larger area. So here we're just going to say that p for this side only is greater than 0.10. You only need to look at one side because the other side is symmetrical. So if that one's greater than 0.10, then this one is also greater than 0.10. So think about this. If you have two areas, both are greater than 0.10, double it. Okay? So basically what's happening in this area, this is only half of your p-value, because this area, the p-value itself represents the entire, both tails together. So one tail is going to be half, because this is a two-tailed test. This only occurs on two-tailed test. The other area is half of your p-value. So that means half of your p-value is greater than 0.10. We're going to double that. So when you double half of p, you get your p. This is a pretty large p-value. It's greater than 0.20. Regardless of what alpha is, let's suppose alpha equaled, I'm just going to make this up. Even if we had a large significance level of 0.10, clearly if p is greater than 0.20, this is how you have to do a little reasoning here. and alpha is 0.10, we can conclude that P, that does not look like an alpha, sorry about that, P is greater than alpha, and in this case, that is a do not reject. So again, calculating everything else is going to be very similar. It's just finding that p-value becomes a little bit more difficult. So let's take a look at the steps. We still have the same assumptions, simple random sample, normal or large samples, but this time we have sigma unknown. Reading your problem, you could still either do a two-tailed if they're different, a left-tailed if it's less, a right-tailed for greater. You still need to write down your information. And let's look what's changed in the formula. Our z clearly becomes a t, test statistic. You still have x bar minus mu sub 0. And notice here, what was sigma is now an s value. So we can take a look at the formula sheet itself, go up to chapter 9, because chapter 9 is the hypothesis test we're working on here. And you can see there's the formula we use. And don't forget, we have to deal with degrees of freedom. Your critical value approach is going to be pretty much identical, just you're taking the value off the t table, not the z table, and your p-value approach we just kind of went over. So let's work out one problem for this before we end this particular video. Here we have a set of data. I want you to take a moment. I want you to look at it. I want you to gather the information and set up the null hypothesis, and then pop the video back on to make sure you have that much correct. So here's what you should have. When you're reading this problem again, just like before, you've got to distinguish between that population mean that we're comparing it against and our sample mean. The population mean is what's going to go into our null and alternative hypothesis. And sometimes this could be data from a larger group. Sometimes it could be data from the past. In this case, that's what's occurring. We have the average person watched 4.55 hours of television back in 2005. And then we want to determine, do the data provide sufficient evidence to conclude the amount watched per day differed from what occurred in 2005. So the one we're measuring against is that 2005 data. So that's why we use the 4.55 when developing our hypothesis. This is going to be a two-tailed because of the word differed. Remember, less would be less than, greater, a greater than. And what's our important information? We have a sample size of 20. The mean is given at the end of the problem at 4.760. The sample standard deviation, so write that as an S, is 2.297. Our significance level is 10%, so that's 0.10. And since we are doing a T, we know we're going to do a T because we're using an S and not a sigma. You need 19 degrees of freedom. So now I want you to stop the video and go ahead and calculate that test statistic. Okay, so I'm getting a test statistic of 0.409 approximately, so hopefully you work that out. As you do more and more of these problems, you will start to recognize, you will almost get a feel at this point whether you're going to reject or not reject. That test statistic is really close to 0, so this is probably going to lead to a do not reject. But let's go ahead and look at our two approaches. So real quick, we will do the critical value approach first. Again, you have to know how to do both, but you will only need to do one. In our critical value approach, we draw our table, we draw our normal curve, and then this is a two-tailed test, so we put our two tails in there. And in the critical value approach, we have to put the critical values as the part that separates that do not reject region from, in this case, because we have two tails, the two rejection regions. So we can get our critical value from our T table. We are looking at 19 degrees of freedom, and we have a significance level of 0.10. So that means that 0.10 has to split because it's two-tailed. This critical value that's going to go here is taken from t of 0.05 or 0.10 divided by 2, because each of these areas is 0.05 when doing that critical value approach. So we have the negative and the positive. Okay, if this were one-tailed, we would look up the 0.10 area on our table, but because it's two-tailed again, you've got to split that area in half and look up 0.05. I want you to go to 19 degrees of freedom and find t of 0.05. Let's go back to our table. Go to 19 degrees of freedom, which is going to be here. T of 0.05 is take a look at that. It's the second column. There's 19, and it looks to be 1.729. So you are going to put that 1.729 and negative 1.729. Our critical value was only 0.4, so if 0's here in the middle, the critical value is going to fall, if this is 0, and that's positive 1.7, it's going to fall probably right around there. Okay, and that is clearly in the do not reject region. Let's also take a look at that p-value approach. Again, draw a picture so you truly understand the difference between these two approaches. You have your two tails. Here's the difference again. When you are doing that p-value approach, it's the test statistic that goes on these lines, not the critical value. We do not get a critical value in a p-value approach. I know that test statistic is positive, but because this is two-tailed and it's symmetric, we're going to put the positive and the negative down. Your p-value is going to be the area that's represented, and this is going to be much bigger because these values will be closer to 0. This is going to be a rather large area. The more to scale you can kind of draw it, the better. Here, I'll move it over a little bit. Because it's going to be so close to 0, I would put it almost here. Not very symmetric, but you get the idea. Now, the p-value is going to represent both of those sides. So basically, if we went like this, your p is both of those together. We can only get half of them right now. So we're going to go again to 19 degrees of freedom, and I wanted to look to see where 0.409 would fall on your table. So erase what we did before. Here's 19 degrees of freedom. Clearly, 0.4 is well before 1.328, and since 1.328 has an area of 10, this is going to have an even larger area, so it's going to be greater than 0.10. So this p over 2, this half of p is greater than 0.10, and this p is greater than 0.10. Together, you want to double them. So you have half of p is greater than 0.10, so double it. P is greater than 0.20. If alpha is 0.10, we can then conclude, you've got to write this these logical reasoning steps out so I know you're following it. We would say that P is greater than alpha, do not reject. And here, do not reject. So to finish this test, our conclusion is do not reject. And then the statement, the interpretation, we would write again, you're just simply restating this sentence at the 10% significance level. The data we do not reject, so the data do not provide sufficient evidence. I'm going to put ... You would finish it off with sufficient evidence to conclude that the amount of television watched per day by the average person differed from 2005. You could say that the amount of, do not provide sufficient evidence that the amount of television a person watches a day is any different than in 2005. Definitely complete it in the context of the problem. This concludes the video for hypothesis testing when sigma is unknown.